So let's stop for a minute. Okay, so let's see how you can actually solve this. And after seeing the results of the user equilibrium, then you'll be able to solve the system optimal one. Okay? So first of all, the first formula is Q1 plus Q2 equals 3,500. Did everyone get that? Yes? Does anyone have problems with why that is? I just want to make sure. Okay. That is because I want to make sure that all the vehicles coming from the left actually go across. I have two roads. They're either going through Route 1 or they're going to Route 2. Okay? That's why Q1 plus Q2 equal 2,500 plus 1,000. So at this point, I'm not losing anyone. I'm not throwing anyone off the road. You can't use my road, go down to the valley. No, everyone has to go through and reach this point. The other thing is C2, or Qmax of link 2, has that formula of UF times Kj, or rho j over 4, which is what we covered earlier. If we put the formula, this formula, U is equal to 100 minus 0.625 K, on top of the formula that we had earlier, which is Vs is equal to Vf minus Vf over Kj times rho, we find out that 100 is actually the free flow speed. Okay? 100 is the speed here. Okay? When density is very, very low, 100 is the free flow speed here. And 0.625, which is the slope, is the ratio of how much, it's the slope, it's a negative slope. It is how much my speed would be reduced due to the additional traffic that I have, additional density that I have, which is K. Okay? So 0.625, if you equate it to Vf over rho j, okay, you have Vf being 100 and rho j, you'll be able to calculate it. After you calculate rho j, which is 160 vehicles per kilometer, then you put Kj or rho j in the equation there. You have Uf is equal to 100 kilometers per hour, and you have Kj is equal to 160 vehicles per kilometer. You end up getting C2 as 4,000 vehicles per hour. That's the capacity. That's the maximum flow that I can get through link 2. After this, I come up with the other formula, which is by definition for user equilibrium. Vehicles will reach equilibrium when they have no incentive to change their routes. That is because the travel time of one vehicle on link 1 is equivalent to travel time of one vehicle on link 2, which means T1 equal T2. Okay? So you have T1 equal T2. You end up with two equations, two unknowns. Those equations would be with Q1 and Q2, and you solve them, and then you get these values. Now, if you put Q1 inside the formula of T1, you get 6.65 minutes. What about T2? What's T2? T2 is the same. So if you plug in Q2 inside the formula and calculate T2, you should get the same. If you don't get the same, then you haven't solved the two equations to unknowns correctly, because T1 is equal to T2. That's how you came up with the second formula. Okay, so do you have any questions? Why is T1 equal T2?
Because they intersect on the ground.
As we said before, in user equilibrium, the vehicles will distribute themselves onto different routes in a way in which all the different routes will have the exact same travel time. That's why T1 equal T2. Even though your original performance functions for the different links are different, they might not be the same distance, they might be slower, they might have different free flow speeds, but the ending result with user equilibrium would be that any road would take you the same exact time. Okay? So any questions regarding user equilibrium? Okay. Now you have a different problem here. The question says 20% of the vehicles in the network are equipped with in-vehicle navigation units capable of displaying personalized routing information that is recommended by a nearby traffic management center in the region. So that traffic management center has knowledge of everyone, but it can only communicate that information with 20% of the vehicles. Okay? What does the traffic management center usually want to happen? System optimal, right? So what they want is system optimal to be in the system. If they can communicate with everyone, then you would just solve for system optimal and then disseminate that information. Let's say you end up with 60% of the vehicles need to use that route and 40% need to use that route. You just send that information. However, here you can only communicate with 20% of the vehicles. Okay? You can't communicate with everyone. So the question is, if the TMC wishes to use the equipped vehicles to optimize the network's performance, what percentage of the equipped travelers should be sent rerouting information and which route should be recommended? Okay, so if you look at the question, basically the remaining 80%, I can't influence them. I can't tell them which route to take. What should I tell the 20% to do? Or, yeah, what should I tell the 20% to do? Or how many of those 20% I should tell them what? So that the resulting total, okay, the resulting total, which is like the 100% of the vehicles, do what I want, or very close to it, which is system optimal. As a traffic management center, you're supposed to come up with a system optimal solution, and then try to see how people originally behave. How do originally people behave? Based on what? We just did it. If I don't give anyone any information, what would they do? User equilibrium, right? So after you come up with your results, you should see how people originally behave, and then you're supposed to use the 20% here to shift the behavior from user equilibrium into system optimal, okay? As much as you can. Your answer should be how many? Yes, a percentage. You know that you can only communicate with 20% of the vehicles. What's the percentage of those vehicles that should be sent to which route? What you should tell them. So it's telling you what percentage of these vehicles should be sent rerouting information. You can leave some of them, like not send them anything if you don't need to. And which route should you tell them to go to? Okay? So you should start with finding the system optimal solution, and then seeing how it is different from user equilibrium, and then think how to use the 20% in order to shift what is actually happening into what you want to happen, which is system optimal. Okay, any question about the steps that you need to follow? Okay, you can start. I'll give you 20 minutes. Or, yeah, 15, 20 minutes. So this was the user equilibrium solution. For system optimal, what you first need to do, as we said, is calculate TTT1 as T1 times Q1. You have the formula of T1 from before. And calculate TTT2, which is total travel time on link 2, which is equal to T2 times Q2. Again, you have the formula for T2 from before. Then you do the derivative of TTT1 with respect to Q1. You get M1, which is the marginal cost of traveling on link 1. And you do the same for link 2, and you get M2 as 6 plus 4 over 4,000 Q2. Okay? Now, with system optimal, as we said before, we're going to equate the marginal costs, because if they're not equal, I can move one vehicle from one of the links to the other one and reduce the total travel time for all the vehicles. So we do M1 is equal to M2, and we have the original formula from before, which is Q1 plus Q2 is equal to 3,500. And when we solve the two equations to unknowns, we get Q1 equals 1618 and Q2 equal 1882. Now, when I plug these Q values in my M1 and M2, I will get the same thing, which is 7.8, which means I'm fine. I don't need to shift anything. I'm at system optimal. What about T1 and T2? T1 and T2 are not the same. If you calculate it, you can tell me I haven't calculated it. But one of the routes is actually longer. So some of the vehicles have to go through a longer route. They're going to have a larger travel time. but that's the only way that we can achieve system optimal. Some people have to suffer a bit so that everyone together can have a total, the minimum travel time. And when you're routing this information again next time, you'll be doing a fair routing so that those people will now be getting the shorter route. Okay, so the other question that we had regarding the what you do now. Okay, so this is the system optimal result. Up there you have the user equilibrium result. Now, I cannot communicate with everyone. I can just communicate with 20% of the vehicles. So what should I tell these vehicles, and what's the percentage of these vehicles that I have to tell them to go to use Route 1 or Route 2? What do I want my queues to end up looking like? Which one? System optimal. So I want my queues to end up similar to this one rather than that. If I don't tell anyone anything, what am I going to end up with? Which is Q1 equal to 206 and Q2 equal 1294. So if I'm able to tell a small number of people to take a different route, what route should I tell them to take? Route 2, because I want Q2 to increase from 1294 to 1882, and I want Q1 to decrease from 2206 to 1618. Okay? What's the difference between these two? 588? Okay. So 588. 20% out of 3,500 is how many? 700. So what should I do then? If I want 588 people to go through Route 2, but and I have access, I can communicate with 700 people. So what should I do? How many people should I communicate with, and what do I tell them? I only want 588 people to shift, right? So what do I do? Do I communicate with the 700? Do I communicate with 588? 588, yes. So the first way of looking at this is we tell the 588 out of the 700 to go to take Route 2, and the remaining, I could either leave them or tell them to take the other route. Now, here's the problem. If I do that, then these 700 people who I'm communicating with will follow what I'm saying, but the remaining, among the remaining, a similar percentage to what I had there will be going through Q1 and through Q2. Okay, so if I actually sum up the results, if I take into account that my total pool now is not 3,500, my total remaining pool is 2,800, then I won't end up achieving this. I will end up with far less on Q2. Let me repeat. I have access. So the assumption is if 3,500 people are acting by themselves, 1294 will go there and 2206 will go there. I don't have the exact percentages. Let's assume it's 40 and 60%. Okay, so 40% will be taking a particular route and 60% will be taking another route. Or let's make it 45 and 65. Okay, 45 and 65. No, 35 and 65. That's why I read out 20% to the other route. However, when I can communicate with 700 people, then the remaining, out of the remaining, I'm going to have a similar type of percentage. So now the values actually decrease. Let me show you this with the numbers. Actually here T1 was 5.94 and T2 was 6.94, so T2 was 1 second longer. So this is what I have with user equilibrium, so 2206 and 1294, and with system optimal, I have 1618 and 1882. What I want as a shift is more people on link 2. Okay? So the diversion needed is 588 vehicles per hour from 1 to 2. Of the 3,500 drivers, 700 are equipped. Okay, but I know that out of these vehicles, so the percentage of people who are going to go to route 1 is 2206 over 3500, which is, we said something around 60 or 65%. Okay? Let's see. Let's see how I can explain this. So, okay. One way of explaining this is I need to, I'm trying to figure out X. X is the number of people I need to communicate with in order for them to shift to route 2. Correct? Now, how many of the vehicles are going to go to user equilibrium? Are going to go to route 1? 2206 vehicles, right? So that's the percentage of the vehicles that are going to be going to through route 1. Now, out of that percentage, okay, I need to get 588 people to go in the other route. So it's not that I want 588 people out of the total, because that's not enough. I want 588 people out of the remaining, okay? So I want 588 out of that percentage to actually go through the route that I want. That's why the X that comes out is 933, which is higher than the 700. So we need to inform 933, which is more than 700. So the best we can do is basically tell the whole 700 to go towards route 2. This will approach us towards system optimal. This will be closer to this, but we won't be able to reach it because we cannot communicate with the 933 required. Okay, let me try to repeat this. Why is it that if I only tell 588 people, it is not enough? Because it is not the percentage that will go to Q1 and Q2. Now, the original way that people were going to distribute themselves was the 2206 and the 1294, right? If I'm removing 700 out of that batch, then only 80% will be going towards the original way. So let's just calculate this. If you do, can someone do this on the calculator? If you do 80% times 1294. 1035. So remember, I'm removing 20%, right? So the remaining 80% that I had, I will have 1035, you said? Okay, so 1035. If I add on top of it the 588, I still am short of this. Okay? I'm like more than 200 short. That's why I need to take into account that I can communicate with 20%, but the remaining, out of the 80%, the exact number of people who are going to go to route 2 is less than 1294, because it's 80% of 1294. That's the remaining. That's why I'm using this formula to make sure which percentage of people that were going to user equilibrium I have to actually shift them. And the total value that I end up with is 933, which I can't reach, but I will settle with something close to it. And it will be, I guess, if we try the 933, it will be very close. It will be around, I guess, more than 1,700 that will be going through user equilibrium. It's far better than, that will be going to route 2, which is far better than the user equilibrium. Do you have any questions about this? Is it clear why 588 is not enough? Originally, okay, I have a percentage out of a pool of vehicles. I have a percentage of vehicles going through route 1, and I have a percentage of vehicles going to route 2. I want people to go more towards route 2. Okay? who am I going to address? I'm going to address the vehicles who are going to route 1 to go to route 2. Now, because this is a percentage, if I'm removing if I'm removing 700 from this batch, because I can communicate with the 700, the remaining 2,800 are going to act based on that percentage, right? So the remaining 2,800 are going to either go through route 1 or route 2. So I cannot assume that I will have 1294 already going to route 2, because that value has gone down. That value has gone towards 1035, right? That's why I'm looking at this, at the whole pool of people, and I'm saying this is the percentage of the people among the, who I'm going to communicate to, okay, that I want them to go to route 2. How many actual drivers do I want to go to route 2? 588. Out of the number of vehicles I'm going to communicate to, that many, okay, that many were going to link 1. If I am communicating with someone who was already going to link 2, then I'm losing, right? I'm not gaining anything. If someone was already going to link 2 and I'm telling them go to link 2, I didn't gain anything. That's why this is the percentage of the people that I communicate to that will actually make a difference. The remaining over 3,500 times x, which is like the difference between this and this, they were already going to link 2. Okay? That's why this value is higher than this, because the remaining ones, the difference between this, which is around 350, those were already going to link 2. Okay? Okay. Now, the last thing we have, okay, I have a few slides here. When is user equilibrium equals to system optimal? Any idea?
Are the same.
When both routes are fully identical, when I have a symmetric network. Okay, so same travel times or same distances, same travel time equations, basically, then I would have the same thing. Another condition that I could have is, think of like a congestion. At what congestion rate would they have similar results? When they're not congested, right? When there's no congestion, when there's no one on the road, you would go through the shortest route. You wouldn't start shifting from user equilibrium to system optimal or from particular routes to other routes unless there's congestion. When there is congestion, you have a diverging relationship between the results of these two. Okay, so this is a way to solve this mathematically, and you can program computers to do this. Actually, Paramex uses similar methods. So for user equilibrium, what you're trying to do is there's a curve, and you're trying to minimize the area under the curve. That's why you have the integral there. And this is the OD matrix. So the OD matrix, this is the link path incidence matrix. This describes okay, let's choose one of them. Link 1, okay, link 1 which is up. Link 1 is on two different paths, right? It's on the path going upwards and on the path that goes through the middle and then goes down. You represent this and you feed it to the computer, and then it can solve it. And this is a similar case. This is for user equilibrium. You can do the integration here. And this is for system optimal. I gave you the simpler way of solving it. Okay. This is the last thing we're going to do today. So Braess pseudo-paradox. I'm going to discuss it. We don't have time to go through it. So you have this originally. And these are the travel times that you have. Okay, so travel time on link 1 is 50 plus x1. X is q. Travel time on link 2 is 50 plus x2. So link 2 is here, link 3, and link 4. Okay? This is what the network looks like. Now, we're trying to figure out, so this is q equals 6, and it wants to go here. Okay? What would my results be? How many vehicles would go through the upper route, how many vehicles would go through the lower route? 50-50. Why 50-50? Because it's symmetric, right? Link 2 is similar to link 1, and link 4 is similar to link 3. That's why they would distribute themselves equally. So by inspection and due to symmetry, I have 3 going there, 3 going there. If I look at the actual numbers, so x1 equals 3, x2 equal, all of the links are 3, and then I can calculate the travel time. So the travel time for, so C1 is the travel time for, is the travel cost for link, for path 1. What does path 1 include? What links does it include? Link 1 and link 4, right? Okay, on link 1, how many vehicles are going through? 3, right? So the time that it takes for the vehicles is 53. And what's the, how many vehicles are going through link 4? Again, 3. That's why I have 30 plus 50. Is correct? 53 plus 30, 83. Okay? That's why the travel time for one vehicle to go towards there or towards there is 83 time units. And for the total travel time, what do I need to do? This is the travel time per link, right? Per one vehicle. I need to do Q1 times C1 plus Q2 times C2. I will get the total travel time. So T1 would be 3 times T1 plus 3 times T2. And then I would get the total travel time being 498. Now, we're going to play around with this network. We're going to add a link here in the middle. OK? We're going to add a link in the middle here. And we're going to run system optimal. And we're going to run user equilibrium. And what's going to happen is with system optimal, I'm going to have what I had before. And this link is not going to be used. OK? This additional link has this cost, 10 plus x5. If I run user equilibrium, what does user equilibrium do? What's the equilibrium state? The equilibrium state is having the same travel time on all routes. From the source to the destination, how many routes do you have? You had 2, now you have 3. 1, 2, 3. Right? So what does user equilibrium do? It makes sure that these 3 routes have the same travel times. So it keeps on adding here so that the travel times that end up on each of the path end up the same. So if you do T3 plus T5 plus T4, you end up getting 92, which is the same as 52 plus 40, which is the same as 40 plus 52. Yes?
Why would someone use that if it's longer though? Like, isn't
The total travel time is the same. Using based on this, the travel time for the vehicle, if you go through there, it's 92. If you go through there, it's 92. And if you go through there, it's 92. Right? Based on rational behavior of drivers, that's what you end up with. So what's the travel time here? So there, the travel times are 83, 83, and this is 70, and this is not being used, although it's 70, right? What user equilibrium does, it equates the travel times. Because it equates the travel times and how the network has been arranged, you end up with travel time of 92, 92, 92 on the 3 path. And then when you calculate total travel time, here you end up with 498, here you end up with 552. What is happening here? User equilibrium is trying to arrange the network in a way because it wants to have travel times to be the same on different paths, but it's doing very, very badly compared to system optimal. I had a result here, and the total travel time was 498, right? We're talking previously about adding highways, adding capacity. When you add capacity, what happens? Usually. Last time, right? Things improve. Things improve when you add capacity. They say there's congestion. OK, let's just add a highway. Things will work. We added a highway. What happened?
Why
because this is the result of system optimal, this is the result of user equilibrium. The t is based on what x you end up getting. So these are the formulas. If x is 3, you end up getting 53. If x is 2, you end up getting 20, for example, on the third one, right? The solution of how much you're using over that link is here. So 3, 3, 3, 3. This was what we had before, right? 3, 3, 3, 3. That's why it's the same values as before. But in here, because user equilibrium tries to equate the path times to each other, so the 3 paths have to have the same time, you end up getting a ridiculously big travel time for no reason. Yes?
Why wouldn't you just make a highway across?
Well, you did a highway across. No. I know. There's a forest there. You can't cross it. And there's a river on the other side. And there's a very big golf course there with people that pay a lot more money than the rest of us, the rest of them. So you can't close that down. So there could be different terrains, and so here, this is what should happen here. You have this situation. This is how people are behaving. You as a planner, what should you do? Get rid of that highway. They did this in Singapore. They closed down a highway because they did the measurements and they saw how people were behaving in a way which wasn't beneficial for them. Everyone was suffering together. Why? Because of rational behavior. Because of selfish behavior. Rational is selfish. Okay? If you're not doing what would be the best for the whole system, all of the users are going to suffer together, and they're ending up having total travel time which is far bigger. Each of them is spending 9 more minutes on the road, right? By trying to compete, depending on what you have in your network, they're actually suffering. Interesting? When I saw this the first time, I was like, I can't understand this. So especially, I don't know, after you learn a bit in engineering, you feel like you can understand stuff. It's intuitive. This is counterintuitive. But this has actually happened. And that's why the next time, I don't know, you're in your family's car and your parents are saying, they should build another highway. Just tell them. Sometimes building another highway doesn't work. They should go and check other things such as intelligent transportation systems, the type of things that we're doing. So what we discussed today in terms of ATIS, ATMS, so on and so forth. Okay, so finally, observations here. The past travel times increased despite the addition of the new highway. Total travel time also increased, i.e. the new highway made the network worse. Explanation, under user equilibrium, people try to act selfishly in order to minimize their own travel time, but there's no consideration of optimizing the whole system, which means there's no guarantee that the total travel time will not be higher, as what we saw now. In other words, the supply action intended reducing the system optimal function, but users distributed themselves based on user equilibrium, which made everyone suffer together. Okay, so not every addition of capacity is useful. On the contrary, sometimes restricting travel, such as using tolling or things like that, would actually make people behave in a better way. And capacity restriction examples, such as ramp metering, tolling, all of those things remove some of the capacity from some of the demand from the road and make you stick to the left side, which is the uncongested state. Yeah, so basically to know which links are useless, you run system optimal, the links that have very low flow, remove them. You go and block that highway because it's not good for anyone. Questions?